Okay, welcome to section 2. We're talking about the strength of the correlation. A correlation exists between two variables when the value of one variable are somehow associated with the value of another. When you see a pattern in the data, you say there is a correlation in the data. Though this book is only dealing with linear patterns, patterns can be exponential, logarithmic, or periodic, like the vibration of a guitar string. To see this pattern, you draw a scatter plot of the data. The words weak, moderate, and strong are used to describe the strength of the relationship between two variables. So let's look at some scatter diagrams. All three of the scatter diagrams in the top row have a positive correlation. That means that as we go to the right, the height goes up. In other words, a positive slope. The first shows a moderate positive correlation. There's certainly a positive correlation, but the data is somewhat well distributed about that increasing trend. You can imagine the residuals being fairly large for that one. The next one is certainly positive and strongly positive. You can imagine a line that is really close to all of those data points. The last one is perfectly linearly correlated in a positive correlation, and you can imagine a line passing through all those points nearly perfectly. Now we can say the same three things about negative correlation. In other words, moderate negative, strong negative, and perfectly negative correlation. Here's one example just to remind you what negative looks like. As you go to the right, you're going down. So as x increases, y decreases. Now there's two other cases, and that is where there's no correlation at all. Not linear, not any sort of correlation. Something that we won't be talking about in this book is other forms of correlation that are not linear. So for example, taking a look at this case, we can see that the nice correlation but not linear. It looks like a smile or a parabola or a hyperbolic curve. The linear correlation coefficient is a number that describes the strength of the linear relationship between the two variables. It's also called the Pearson correlation coefficient after Carl Pearson, who developed it. The symbol for the sample linear correlation coefficient is R. The symbol for the population correlation coefficient is rho. R is always between -1 and 1. If R equals -1, then there is a perfect negative, that means downward, linear correlation. And R equals 1 means there is a perfect positive, that is upward correlation. The closer R is to 1 or -1, the stronger the correlation. The closer R is to 0, the weaker the linear correlation. But be careful, R equals 0 does not mean there's no correlation. It just means there's no linear correlation. There might be a very strong curved pattern. Looking back on our beer example, if we select both columns and do a two-variable regression analysis, we see that the calculator gives us R. Notice that when we choose a regression model, it also gives us R squared. Now, as always, correlation does not prove causation. However, if there is a lack of correlation, there's almost certainly no causation. It's difficult to establish causation by observational data like regression analysis. Remember, this is classical statistics, and this is exactly what you'd expect in a classical statistics setting. Of course, we know that there's also Bayesian statistics. A properly designed experiment is used to establish causation, although sometimes even a classical statistician will acknowledge that sometimes observation is the best that we can do. The example of this that we've been using all semester is ice cream and drowning. There is a very strong positive correlation between ice cream consumption and drowning deaths. And of course that's because of summer temperatures. There's that lurking variable that causes both to happen at the same time. Explained variation can also be found from our calculator. The total variation, that is, all those differences between the linear model and the data itself, can be broken into two parts. That is, the explained variation and the unexplained variation. The unexplained variation could come from other parts, but the explained variation is from the model. In other words, the difference in the data that is explained by the linear model. Now that proportion of the variation that is explained by the model, that percentage, is the quotient of the explained variation over the total variation. And that's r squared in your calculator. R squared is the coefficient of determination. Now this notation is nice because r squared is the square of r. So if you know what r is, you simply square it to get the coefficient of determination. And similarly, if you're given the coefficient of determination, you can take its square root to get r. Now, there is no r for nonlinear correlations, but there is still a coefficient of determination. Looking back at the beer example, we can see that r is 0.9134. So in our calculator, we can simply take 0.9134 and square it to get r squared. Thus, r squared is 0.83429956. Thus, about 83% of the variation in the calories in beer is explained by the linear relationship between alcohol content and calories. The other 16% of the variation is due to other factors. So we used that random sample of different beers' alcohol contents to put in two different lists, and we plotted it. We found the outliers and removed them. We see that it's a random sample. Now let's look at the correlation coefficient r and the coefficient of determination r squared. And important in this question is to interpret them, to say what they mean. So when we saw in our calculator that r equals 0.91, that means that there is a strong linear relationship. You can say a strong positive linear relationship. Strong because it's very close to 1. When we looked at r squared, we said that r squared was equal to 0.834 approximately, and that means that 83.44% of the variation is explained by the linear model.